Hey everybody, welcome back to Organic Chemistry. Now we're doing Aromatic Systems Part 1, Section 3. My name is Todd Rothman, and in this video we're going to go over the criteria for aromaticity. So at this point we understand a lot more about the orbital, we understand what makes up an aromatic system and some of the general ideas about that. Now we're going to figure out when things are aromatic. And what we're going to do is we're going to consider a few different things. Number one is the basic rules. Then we're going to go on to something known as non-aromatic and anti-aromatic, and we're going to understand the differences between them. We'll talk about what's called annulenes. Annulenes are monocyclic systems. Benzene is an annuline, for example. Or any ring, any single ring system is known as an annuline. Aromatic ions, and then finally problems to wrap up. Let's get started. So the first thing I want to talk about is the rules of aromaticity. Let's use benzene as our reference so we can see that we know this is aromatic. Let's follow the rules to see why. The first rule is that it must be cyclic. All aromatic systems are cyclic. If it's not a ring, it cannot be aromatic. Okay? First rule. And the reason why, by the way, is because we know that circulation, remember that 3D animation I showed you, you need to be able to circulate all the way around electrons, and you can only do that if it's a ring. Number two, it must be planar. Now, what does that mean? Well, in order to be planar, that means that every atom in that ring must be sp2. Okay, so one obvious way is sp2, or sp, or, now here's the thing, a lone pair. Now, a lone pair allows it to become planar, and we'll see why when I get to lone pairs at the end of this video. But it allows it to be planar as long as the lone pair that's conjugated to a double bond, because then you can think of it as planar. See, sp3 carbons are not planar, and so they can never be aromatic, right? So for example, if I have this ring, double bond, this is not aromatic. Now why? It's cyclic, right? But this carbon here is sp3, and so is that sp3. They're not double bonded, so this cannot fully go around into a circle, so it doesn't have that circulation that aromatic systems have. So the fact that these two carbons don't have a double bond means that it's not aromatic. Now I'll tell you, if I had a lone pair here and let's say a positive there, yeah, that's aromatic, because a carbon that's positive is sp2. You have to remember that. A carbon that's positive, sp2, and this right here is a lone pair, and since it's next to a double bond and next to a positive, it can do resonance around the system now. So you can allow things to become aromatic if it has a lone pair, or if it's positive carbon and it's next to double bonds, then it's possible. Okay, but if it's sp3, it is not aromatic. All right, so that's the idea for rule 2. Rule number 3. Rule number 3 says that it must be completely conjugated around the ring. Now, it doesn't matter if, and by the way, let me just make that clear, the peripheral of the cyclic system. So in other words, if I have, let's say, a ring system like this, okay, and there's a double bond, double bond, double bond, double bond, double bond. Well, this is cyclic, and it's completely conjugated all the way around. So this, notice how, what I mean by conjugated, I mean that it alternates between double and single bond, or a lone pair and double bond, right? So if there's a lone pair, it has to be next to a double bond. So there's a separation between the lone pair, the double bond, by one single bond. That's conjugated. Conjugated in the double bond sense is where there's an alternating double single bond characteristic. Now, if I happen to have, let's say, a ring over here, so by the way, so this is cyclic, it's fully conjugated, and so everybody's sp2, right? Every atom is double bond, so we're assuming that this is going to be aromatic. Now, there's some tricks to this, which I'll get into later, not now, to figure out some more details. But for now, let's just assume it is. Now, if I have a ring like this, and a ring like this, and a ring like that, and a ring like that, is it aromatic? It is. See, the thing is that we don't care about all this stuff. We only care that the ring in this system here, this ring right here, is conjugated, cyclic, right? We don't care about any of this stuff outside, because this is the ring right here that's aromatic. All this is fluff. It's just connections around it. And you can have connections around it that are not conjugated, provided that the ring, that you can find a starting point and go all the way around a loop back to that starting point, and everyone is cyclic, it's conjugated, planar, and so on. Okay, so this is aromatic. Yep, this is definitely aromatic. Even though it doesn't look like it's aromatic, it actually is aromatic. Okay, so that's what I mean by the perimeter. So the perimeter of the ring itself. We don't care about all this other stuff that might not be. All right, you'll see more examples of this soon. Okay, so that's that right there. And let me just emphasize again, if you have, let's say, a ring system like this, and there's a double bond here and here, and a lone pair, well, this is fully conjugated. Because this right here, these are definitely conjugated. You can see double bond, single bond, double, but when you have a lone pair, if it's right next to a double bond, it's conjugated. So this is cyclic. Now, is it planar? Well, these are definitely sp2. Now, this carbon on top, this you might think of right here as sp3, because it has a H, 2 single bonds, and a lone pair. Normally, we would say that's sp3, but the fact is that it goes in, it has resonance, it'll become sp2. So that's why for this rule over here, where I say it must be planar, it's either sp2 double bond, sp triple bond, or an atom with a lone pair that's conjugated. So that's what we're seeing here. So this is cyclic, it's fully conjugated, and it's going to be, and it's planar. Everybody has sp2 or could be sp2 form. And so yeah, this is also aromatic. This is aromatic. Okay, so far so good. I hope that's clear. So number 1, cyclic, 2, planar, 3, conjugate, and then finally number 4 is known as Hckels Rule. Hckels Rule. And this is called the 4n plus 2 rule. Now, a lot of times people get confused. What is n? Okay, now I have an easier way for you to know the Hckels Rule, but I'm just going to explain to you from the way that you learn in your book. Now, n is any integer, any whole integer. It cannot be a fraction. So it could be from 0 up to infinity. It doesn't matter, but it has to be a whole number. 0, 1, 2, 3. It can't be 0.5. It can't be 1.5. It has to be any whole integer. Okay? Any whole number. Now, what we do here is the 4n plus 2 equals the total number of allowed electrons to be aromatic. Okay? That's what this means. It's the total number of allowed electrons. And you could plug in to be 0 and up. So 4 times 0 plus 2 is 2. So if you have a system with 2 electrons, it's going to be aromatic if it follows rules 1 through 3. Okay? Here, how many electrons are in here? There's 2 for this double bond, another 2, 4, and then another 2, 6. So 4 times 1 plus 2 equals 6. So this is equal to 6 electrons, and you can get that by 4 times 1 plus 2, right? So now I know this is aromatic. Number 1, it's cyclic. Number 2, it's planar. Everybody is planar. This doesn't look planar, but remember, a lone pair next to double bond is planar. You could think of it as planar. Same thing with a cation. Same thing with a radical. As long as it has something next to a double bond. So maybe we should write radical up here. Lone pair or radical. I'll just write it for yourself. Or radical. Because radicals, well, I mean, you should write it. So let me just do it. Or radical. Okay? Or radical. Now, it's completely conjugated, right? So it's got full conjugation all the way around. and it follows Hckels Rule. Now here's an easy way to figure out Hckels Rule. Here's the easy